And today's lecture is about my hobby, my passion, so I'm grateful for the Science Foundation for having me here. Now, this is waves inside stars. Now, stars are spherical bodies, so where to start? Well, at least some of you, most of us, are familiar in some way with waves inside the Earth, right? That's a spherical body, and it has waves created by earthquakes that propagate into the interior of our planet and that allow geophysicists to derive the physics and the chemical properties of our planet. Wouldn't it be great if we could do the same for stars that are also spheres but gaseous bodies? And if you wonder if we can do that, well, since I'm standing here, yes, we can. We can do that nowadays. As you can see here, for one star in our galaxy, upper graph where I show its brightness as a function of time during 15 days, uninterrupted measurements of the brightness of the star that changes because it has star quakes going on, okay? And so if you look at the comparison, well, these seismic signals are not that different from each other. So the techniques that geophysicists developed for seismology of the Earth are somewhat comparable to what we do for stars. So nowadays we can really look inside stars. That's incredible. It wasn't possible several decades ago. And as always, if you open up a new window, because now we can look inside the stars, then you hit some surprises. And some people are then a bit sad that the beautiful theories that have been used do not work perfectly. But I belong to the group of people who are happy when it doesn't work, because then we can learn something new. Okay, so I want to try and communicate that to you. Why do we want to bother? Why do I want to bother? Well, I guess most people want to know what our origins are. And here you see a beautiful table of Mendeleev, tuned to the astrophysics version, let's say. And so all these beautiful elements are created thanks to stars, except for the Big Bang elements like hydrogen, helium, and lithium. All the chemical elements are made up in stars. They evolve, they create it by nuclear fusion and give it back to the interstellar medium of the galaxy, and then new stars are formed, and we have this chemical cycle going on. So we understand pretty well how this chemical table comes to be, but there are major uncertainties, mainly in the merging neutron stars that have only been observed very recently, thanks to multi-messenger physics, gravitational waves. These are big uncertainties due to nuclear physics for that type of objects. That's not my specialty, so I'm not going to focus on them. But all the other three here, like massive stars, low mass stars, and exploding white dwarfs in binary systems, these are all made up of stars that have chemical factories throughout their lives. And the uncertainties in this diagram come from our limitations in the evolution of these stars. So I could have plugged another Mendeleev table, also made by astrophysicists, but then the color coding would be somewhat different and quite different in some aspects, some elements. And that's because our models of stars are not perfect. And so just as waves in our planet allow to improve models of our planet, waves inside stars allow us to improve models of the stars, where we can't put our equipment to measure the seismic signals, right? So we have to find something to improve that. So recap, for those not familiar with astrophysics, stars rule the chemistry of the universe. And they do that differently depending on whether they are stars like the sun. The sun is just a tiny little star for me, yeah? With about 10 to the 30 kilograms of gas, yeah? That evolves. But the more massive stars, they are way more capable in creating heavy elements, typically beyond carbon, nitrogen, and oxygen, yeah, all the way up to iron. So in terms of chemistry of the universe, it's the massive stars that are more important. But there are way fewer of them than there are sun-like stars. So this cycle of chemistry here that you see schematically here, the details do not matter that much for you here in this lecture. We have to sort of like make a distinction between stars that are pretty similar to the sun and their descendants, yeah, and stars that are born with a lot more gas. Yeah? And these tend to explode at the end of their life, as you see here, as supernovae, or leaving behind neutron stars or black holes. Yeah? So if we look at this table, then actually, what is the biggest uncertainty in the color coding and the galactic chemical evolution of the Milky Way? Well, the biggest uncertainty, aside from nuclear physics aspects, is mixing of chemical elements inside stars. And this is both in single stars and in close binary stars. And this is where waves help us. So that's what I'm going to be focusing on. Now, my playground as an astroseismologist is stars that have star quakes. Huh? These are stellar oscillations that we can measure and interpret. And we have been able to measure that for stars with masses between 0.7 solar masses at birth and about 25 solar masses, and gradually moving upwards. Yeah? So in terms of the chemical evolution of the Milky Way, it's also important not only the mass at birth of a star, but also how long it lives before it gives away all the metals that it made. These are really metal factories of the universe, you could say, before it gives that back for the next generation of stars. Now, the lower the mass of the star, the longer it lives. That's because it's not consuming that much energy. So in terms of masses, if I look at the lower mass stars where we still detect star quakes, well, this is still the first generation after the Big Bang, actually. While these huge, massive stars, like this one, well, we have thousands and generations that have already gone dead and have given their metals to the universe, right? So in terms of evolution of chemistry, well, there are few of those, but they live and die fast. And so they are very important, right? Here, below the solar mass, the stars, they live very slowly, calmly, and mainly deliver carbon to our universe, but there are plenty of them. Huh? So that's a bit of the thing you have to keep in mind. Yeah? Now, stars like the sun, I don't know if you are familiar, but they rotate very slowly. The sun is just a slow rotator. It takes about 26 days to revolve around its rotation axis. Stars that are much more massive than the sun, they rotate fast. Yeah? They are not slowed down by a process called magnetic braking. And because of that, we also have to keep in mind the interplay between rotation of the gas and up and down motion due to the oscillations, okay? And so stars really can rotate either almost not. The sun is a very slow rotator, but there are stars that take hundreds of days to rotate, or almost at critical. And with critical rotation, I mean that the star is spinning up so fast that the centrifugal force is overcoming gravity, and then you don't have a star anymore, okay? And so we see all these possible rotation rates, right? Now, I do have to show an equation, because this is a colloquium about waves, so here's the wave equation that I'm using, right? What do? We assume that the star is a spherically symmetric ball of gas in equilibrium, and when it has seismic activity, the gas moves up and down in a complex way, which can be described beautifully in terms of mathematics by spherical harmonic functions, because in equilibrium it's a sphere, right? And that's a very good approximation. Right? If you look at the sun, of course, never without protection glasses, then it looks pretty spherical, right? So we can do that. Now, the wave equation then can be written as here, where this psi here is the displacement when the star is going up and down. It has hundreds of star quakes going on, yeah? And they displace the gas and create waves that travel inside the star, right? And so, assuming a spherically symmetric star in equilibrium, and another major assumption is that this, I mean, I'm using my hands all the time, but I'm exaggerating largely, right? Because the up and down motion due to stellar oscillations is actually tiny. So we're working in a linear approach, assuming that the up and down motion of the gas is tiny compared to the stellar radius. Huh? And then you can make mathematical approximations that look like this. And then the waves have a certain frequency, denoted here as omega, yeah? And a spatial part that is described by the spherical harmonics. And you see some color-coded spherical harmonics drawn here, where a three-dimensional body that is deviating from its equilibrium, you have three numbers to describe the nodal lines, as we call them, of the displacement due to each star quake. So each graph here represents one type of oscillation. And you see these white bands here. There, the gas doesn't move. The red parts, when it's oscillating, is moving actually away from you as observer, and the blue parts are moving towards you. They are blue shifted and red shifted. That's why we chose these colors. Okay. Now you can see that these spherical harmonics are characterized by different nodal lines. So this is an L equal 2, a dipole mode as we call it. This is a quadrupole mode. This is a dipole mode when there's only one nodal line. This is one with two nodal lines, but they are differently placed compared to this one. This is a sectoral mode. This is a zonal mode of L equal 2. And then the higher your degree for the mathematicians in the room, the more complex this function becomes. And you, as an observer, as an astronomer, at the telescope or in a space mission, you do not see the stars resolved like this. So it's fairly difficult to find what kind of mode is ongoing, particularly if you have hundreds of them beating at the same time, okay? So that's an aspect we have to try to understand. To make that a bit more clear to you, here are some movies. So the previous slide had just a snapshot. Now, all these oscillations have their own frequency, and so the motions towards you and away from you, they change in time, and they do that with a certain periodicity. That's the frequency of the oscillation mode, right? And so here you see some low-degree modes. This is a high-degree mode, many surface nodal lines. And then if you have all these patches, yeah, if your gas is moving away from the center, it becomes a bit cooler. If it's moving towards the center, it becomes a bit hotter. And that's why you see the star quakes in the light curve, because you make it slightly hotter and cooler, and that changes the brightness of the star. And if you have an instrument that can measure that with high precision, that's how we measure the oscillations of stars. And astroseismologists are people like me who detect oscillations of stars and interpret these waves that are bouncing back and forth inside the star and that make the surface move up and down, okay? We can do that since several decades now with a precision, typically parts per million. So 1 in a million change, we can detect that, right? Now, if we look at the waves and the frequencies that you can have, then you can have slow waves and rapid waves, right? So this is drawn on a very simple axis here where you see the frequency, and the high frequency regime, there the wave equation is actually dominated by forces that are connected by the pressure force of the gas. So these are acoustic waves that you all know very well. I'm creating them right now in this mode cavity, let's say, right? So that's a high-frequency limitation of this equation. And as mathematicians like, we make all sorts of limits. High-frequency limit, low-frequency limit. Now, high-frequency, let's think of the sun. The solar oscillations have typically a periodicity moving up and down of about 5 minutes, right? And the rotation of the sun is 26 days, roughly. So when you study the oscillations of the sun, well, the gas bounces up and down and the waves travel with a period of 5 minutes. And it takes 26 days to revolve. So it's a pretty good assumption mathematically to assume that the sun is not rotating, right? Because 5 minutes over 26 days is a very, very small number. But there are also stars who are at the low frequency limit with their oscillations. And so stars have typically rotation periods of the order of days, right? Can be 30 days like stars for the sun, but it can also be 1 or 2 or 3 days. And then the waves themselves caused by the quakes, yeah, these also have periodicities of the order of days. That means that you can no longer assume that the star is not rotating when you study their oscillations, because you have basically the same order of magnitude. So that's a lot more difficult to do the study of waves in these stars when their frequencies are here, right? And then you have to take into account this term here, which stands for the Coriolis force, right? For stars that rotate even faster, they get flattened by the centrifugal force. And then it becomes a whole lot more difficult because then you lose the capacity to describe everything in terms of a beautiful spherical harmonic because the equilibrium star is no longer a sphere. We are not yet at the stage that we have fully developed astroseismology of flattened stars. I'll come back to that because that's something I want to do. All right, so how do we work in our daily work as an observer? As said, you can't resolve the star. It's just a tiny little dot in the sky. Yeah? So you have to do with the seismic signal that you get, like in this light curve. Yeah? And this is 15 days plotted as seismic activity. In reality, we don't have 15 days. Thanks to the NASA Kepler space mission, we have 1,500 days. But that wouldn't be a nice, pretty picture. Yeah? So I just gave a small part. Now, what do we do since the time variability is sinusoidal in the linear approximation of oscillations? We Fourier transform this light curve. Mathematicians and engineers as well, they love Fourier transforms. And that gives the graph below here. So here you see the amplitude of the oscillation as a function of frequency for this particular star that has been observed by the Kepler mission. And you see all these beautiful frequencies of waves that are always going on inside the star. Right? Here, the star has a strength, the strongest waves, you could say, around 75 microhertz in this case. Yeah? So again, the sun, that's very different because then you have 5 minutes and it is 3 millihertz, 3,000 microhertz. Okay? So by looking where the quakes have their strongest frequency, you can immediately say, more or less, how big the star is if you compare it to the sun. And we know how big the sun is because we can literally measure it in the sky. Okay? So this already tells you that by Fourier transforming the light curve, I can deduce how big the star is fairly easily in a rough way. But what we really want to do is, as this animation shows, is dive deep into the star and derive the physical and chemical properties as close as possible to the stellar core where the nuclear fusion is going on, because that's where the life is directed. Yeah? Now, in terms of chemistry, let's say we have a chemical species, different kinds, inside such a star that has many starquakes, but here I only draw one. What changes the chemical composition in the layers of the star? Well, first of all, there's nuclear burning. Right now, the sun is transforming hydrogen into helium in its core, so it's losing hydrogen in terms of mass fraction at the advantage of helium. there can be mixing, and that's what we don't know very well. But there's also changes in the chemistry, layer by layer, due to microscopic phenomena, like heavier material sinks and lighter material rises in the gas. You know that very well. That's settling or radiative levitation. And then there's also all sorts of macroscopic phenomena of the fluid elements. So stars rotate. We can see that for the sun at the surface, but that doesn't mean that the rotation inside the sun is the same as at the surface. Why would it be? On the other hand, if you don't know how it works, internal rotation, then we just assume that it's the same deep in the interior than at the exterior, because if you don't know how it changes, what would you have to do? And this is a very important thing that we manage now to deduce. So the theory is there of all these physical phenomena, but the theory is uncalibrated, basically. In principle, if we were to know it perfectly well, then we would not need observations to test the theory. We could just make predictions based on the theory. But reality is different, and this is where waves inside stars are really the big advantage that we have since, well, more than a decade now. Why do I like this research field so much? That's my hobby. That's one reason, but also because it's very transdisciplinary. So asteroseismologists really couple theory, basic laws of physics, conservation laws, where any gaseous sphere has to adhere to, right? To new observations that are typically the seismic observations, the brightness measurements that we can get, and to hydrodynamical simulations that are a fantastic tool with modern computers, but we can only do that for a snapshot in the life of the star. We cannot do that for mimicking billions of years. So there is an interplay here that we have to take, right? And the astroseismic modeling is basically circling around in this spinner. I love spinners. And we use data and equations that have forces, that have surface measurements of stars, and that have the oscillations, mainly the frequencies. So that's what we're using daily, so to speak. So from the observational side, we have beautiful space photometry, and this got actually kick-started by the CORO mission in 2006. That was a French-led European mission. Was a bit of a proof of concept satellite, if I can call it like that. And then came, of course, the beautiful NASA missions, Kepler and TESS. Kepler was operational from 2009 up to 2013, right? And now, literally now, TESS is measuring for us. These are all missions that are specially designed to actually not do astroseismology, but to hunt for exoplanets. Because, well, it's easier to pay a mission to hunt for extraterrestrial life, to be honest. And so that's fine for me. The planet hunters can have the planets as long as I have my starquakes, right? It uses the same, it needs the same type of measurement. So fluctuations in the brightness over a long period of time without interruption, so that we have a beautiful Fourier transform with cleanly selected wave frequencies. Now, of course, we tried this from the ground prior to the space era, and then we can detect stellar oscillations from the ground, also non-radial oscillations. But if you are an astronomer to do it from the ground, you go to your telescope, you observe during the night, if you are lucky, if the weather is cooperative, if there is no technological problem, etc. But in any case, during the day, you can't measure the stars, right? They are there, but you can't measure them. So you introduce periodic gaps in your measurements. That's a pain for people like me, because it mixes up all the daily life of an astronomer in terms of periodicity and the stellar oscillations in terms of periodicity, right? So this field actually only made progress since about 15 years, where we have this uninterrupted data that then give these nice Fourier transforms. And here for these stars, this is a star about twice as massive than the sun at birth. And you see, you can count where my pointer is. It has tens of stellar oscillations. Yeah. Now, we can only interpret the physics and the chemistry if for each of these frequencies, we can label the spherical harmonic. We have to know which spherical harmonic causes that particular frequency. And this is the tricky and hard part. Yeah? So we need not only observed frequencies, but we also must know what type of quake they correspond to. Yeah? Now, on the other side of this graph is the theory and the simulations, yeah? Where you have, for a certain stellar mass, every star has a mass at birth, for a certain age of the star, it evolves throughout its life, and for a certain chemical composition, these are minimally the parameters that you're dealing with, that you're trying to estimate. But there's a whole lot of physics ingredients, as I said, that you don't know. And these you have to sort of try to describe, and that's being done in stellar evolution models by parameterized laws, because we don't really know how stars rotate in their interior. We don't know if they have a magnetic field, and if so, what its shape and strength is. We don't know how the chemical mixing happens, etc. So that's why I've put this in red. These are all phenomena that we know are ongoing and that changes the chemistry inside the star, but we don't know really well from first principles how it works, so we parameterize that in terms of free parameters that we then estimate. And so for such an assumption, you make a stellar model. And the stellar model we assume to be spherical, as I said, right, as a first approximation. This is a major assumption, assuming that stars are spherical. Now, for such a model, we can then initiate a computation of the wave equation by assuming that each stellar oscillation makes the star deviate from spherical symmetry with a certain frequency depending on the spherical harmonic. Yeah? And so we compute that for the mathematicians in the audience. That's actually a beautiful eigenvalue problem. And you look for the eigenmodes, which are the geometrical parts of the displacement, and the eigenfrequency, which is the frequency of the wave, right? And so you have theoretical predictions, an infinite number of eigenvalues, but of course you must be able to label these two to compare. And that's the tricky part of the mode identification I was telling you about. Now, here is an early application, and I show this particular star. We give stellar names in catalogs. That's a bit boring, but they have telephone numbers. Yeah? And why do I show this star? Because, well, it's my favorite star. My supervisor, whose name you see here, started observing this star, which is a massive star. It will later on explode as a supernova. Started measuring in 1983. This is ground-based seismology. And it took us like 21 years to deduce the internal rotation of a star. And this was the first one different from the sun, right? And we found from the shifting of the frequencies, you have to imagine, again, the analogy with sound waves, rotation, when the star is moving up and down, it shifts the frequencies of the waves. That's just like I would sound differently for you when I would be on a podium that would rotate. It would sound awful, actually, for you. Why? Because the sound waves that I'm creating would get shifted towards you and away from you, and it gives a frequency shift. That's what you see here. This is a dipole mode, but it has a component shifted away from you and towards you, right? So as you will have seen in these animations, you can have waves that move against the rotation and along with the rotation. And we call these prograde and retrograde modes, right? And so this shift is tiny, but you can measure it if you measure long enough. And the frequency precision scales as 1 over the total time base. And 1 over 21 years is a hell of a small number, right? So a very high precision measurement, but in all these 21 years, we had more interruptions without data than data points, right? And so it was still a breakthrough that we could measure this, and we found that for this star, which has a mass about 9 times the mass of the sun, the core rotates about 4 times faster than the surface. Yeah. So why is that? Well, stars, when they evolve, their core shrinks because they have to make it hot enough to do nuclear fusion. The outer layers then swell. Conservation of angular momentum imply that you expect a faster rotation. So this made sense, okay? Now, this was just one star. What we do now, we have a whole battery of artificial intelligence and machine learning methods now, because we cannot look at each and every light curve of these space missions. There are millions of light curves. We are swamped with data. We have way more stars than astronomers to analyze them. Yeah? So we need some help from computers, and nowadays we try to find among the millions of stars delivered by these 2 space missions, and thank you, NASA, really, thank you, that we are allowed to work on these public data. That's very important for me. But we need to find which stars are giving us appropriate seismic signal to work with. And among the millions, there are a couple of thousand, and we need to find them. Okay. This would be a whole lecture by itself, but nowadays we get some help, and we do typically supervised and unsupervised clustering methods. How does that work? Well, we see seismic signal. We know some stars that have oscillations. We throw that in a computer, and we let the computer find out which light curves behave similarly, and that's how we find our stars. Okay? Now, here is the easiest application of the wave equation inside a star. Here is the wave equation where I've deleted the Coriolis force, and I can do that for stars like the sun. Again, as I explained, 5 minutes divided by 26 days, that's almost 0, right? So you can ignore the Coriolis force. And here are stacked stars whose Fourier transform you see. These are evolved suns. These are red giant stars. So when the star will have no longer hydrogen in its center, it will start to swell up. The core will shrink because it wants to make it hotter to burn helium into carbon, but the outer layers will expand. Yeah? And so it will become a bigger star. And this happens, it's not going to happen tomorrow, so no worries, but these stars have undergone that. And these are their stellar oscillations. You see the frequency of the oscillations here, and it shifts from about 250 microhertz for this star up to all the way here, look around 50 microhertz. So what is happening here? You have a star with seismic activity, and one of these stars is like this, and the next one, I'm going from bottom all the way up, is a bit bigger, and a bit bigger, bit bigger, bit bigger. What happens with a musical instrument, if you make it bigger, the frequencies go down, right? So this is what we're witnessing here. Stellar evolution in action takes millions of years to go from this evolutionary stage to that one. The stars get bigger, and we can measure their radius very accurately. 2%. Why is that? Because these stars behave like the sun, and we know very well how to do helioseismology. We have known that for the sun since like half a century now. Yeah? And you can scale these stars that have acoustic waves, just like the sun, according to their size. And that's what you see in these equations here. We call them the, how should I call it? The scaling relations, huh? Where the symbol here with this dot here is the sun. So we just scale the star's radius with respect to the solar radius. And we know that the frequencies scale according to the size of the musical instrument that creates them. Huh? You can only not hear the sound because there's no medium between us and the star. But you can scale the radius perfectly from scaling the frequencies. Okay? That's the easy case. Why is it easy? Because the sun is pretty spherical and it rotates very slowly. So then we can afford to take this term, only the gas pressure force and the gravity. The sun has a magnetic field, but the influence of the magnetic field on the oscillations is really very low, and the influence of the rotation on the oscillations is also very, very low. So we can afford to simplify the wave equation. Now here's another bunch of stars. It's completely the opposite. These are stars that have slow waves. Seismic activity at frequencies, well, let me explain where you see what you see here. So about 7 stars, the gray dots are the data that come from the satellite, in this case Kepler, and the red is the Fourier transform of the light curve, okay? And you see, we go from upper left to lower right. But now we're not seeing the stars become bigger. No, these are stars that rotate very fast. And with very fast, I mean typically of the order of a day. And the oscillations, the waves, have frequencies also of the order of a day. So you have to take care of the Coriolis force now. This is a critical force. And then this equation to solve here becomes much more difficult. Even though you add only one force, the differential equation is really more difficult to get a handle on, right? And so what you can see here is that this star is a very slow rotator, yeah? And this one in the bottom is a very fast rotator. I know that now because I've been working on these stars for 10 years, yeah? So now this is increasing rotation rate going from here to here. And what kind of rotation rate? Well, these are modes that are dominantly stored by buoyancy. And so they probe really the deep inner layers of the star. So we're actually measuring directly from the Fourier transform how the stellar gas is rotating near the core of the star, where all the life is directed. Yeah? So I still find this amazing by the day. We look at tiny little dots, we measure their seismic signal, and we know how fast they rotate in their interior, deep inside the star. And that determines how your chemistry mixes. Yeah? Because if you rotate faster, then all these chemical elements get mixed much more efficiently. And that means that you bring more fuel to the nuclear reactor of the star, which sits in the deep interior. And if you bring more fuel, because you mix efficiently, then your star can live longer. And so this has a huge impact on the amount of helium that you create, and it has a huge impact on the age of the star, okay? So this is a new way. We didn't know how to deal with this type of data because we only started finding these data in 2016. So the past 5 years have seen an immense development of astroseismology of rapid rotators. And that's what we call gravito-inertial astroseismology, because the periodicity of the rotation and of the oscillations is about the same. And that's what makes it mathematically more difficult. But we can handle it now. And let me show a diagram that actually, I'm always happy when I see this diagram. What does it show? The internal rotation frequency of a star as a function of its gravity. And this x-axis here is actually the evolutionary status of the star, because the gravity of the star goes down as the star becomes bigger as it evolves, right? And so here you see all the rotation rate of about 1,800 stars that you show here in different color codes. And these are all young stars, higher mass than the sun, right? These are evolved red giant stars. These are stars that the sun will become later on when it has no more nuclear burning. And you see an immense difference. Rotation rates from 0 to about 30 microhertz. So that's very fast rotation. And stars get rid of their angular momentum, as we call it, as they evolve beyond the core hydrogen burning. Now, I've indicated here one star that makes me really happy. That's indicated in blue. The different colors depend on the mass of the star. So the grays are typically 1.5 times the solar mass. The purple are typically between 3 and 9 times the solar mass. And this blue one here is 12 solar masses, because we are transforming from Kepler data, many, many stars, 200,000 during 4 years, to TESS data. Even many more stars, 200,000 to 10 million stars. But Kepler gave us 4 years uninterrupted data, and TESS is giving us data that go from 27 days uninterruptedly up to 1 year. Yeah? So it's much shorter in duration, and 1 over the duration gives the frequency precision. So the frequency precision for test data is lower than for Kepler, but we have 10 million stars instead of 200,000, okay? And so here you see, from these 200,000, we have about 2,000 with a measurement of the internal rotation now. You have to imagine that up until 6 years ago, this diagram was completely empty. We didn't know, well, there was one star, the one I showed in the beginning, where it took us 21 years to get the internal rotation frequency, and if you're in a career, you don't want to wait another 20 years for the second star, etc. So this is a booming field right now, and this star is not yet public, but it will soon be, and it's a supernova progenitor. So we're gradually moving up to higher masses to populate this diagram, and that's really fantastic, because we know now how the gases rotate. A big surprise came when we then not only have the internal rotation of the star, but also the surface rotation. Because, as I said earlier, conservation of angular momentum would make you think that if a star shrinks its core, expands its outer layers, its surface rotation should be way slower than its interior rotation, right? Conservation of angular momentum that ice skaters know so well. Well, if you look here, these are all the stars, and we have about 115 of them only, where we have both an envelope rotation at the surface, say, and an inner rotation. So that's the circles. And they are connected by lines. What do you see here? Well, you see that the core rotates faster. That's what we expect. The surface rotates slower. But in the theory of conservation of angular momentum locally, you would have a factor 100 difference typically, right? This is not 100. For these stars, it's almost the same. This means that our theory, that's what I said in the beginning, we need calibrations because we don't know very well how these laws behave. And it seems that most of the stars have rotation in their inner part, which is almost the same as the outer part. So the factor 4 we had prior to space asteroseismology was pretty high for that star. Most stars have a lower differential rotation, as we call it. And this gives rise to an immense amount of work, new theoretical work, new simulations, of which some across the street here. That is beautiful because this helps us to understand the physics of the interior rotation way better. Yeah? And so there's really much theoretical progress ongoing where magnetism is a very important force that we have to include in the wave equation, but also in the equilibrium equation of the star, and also the transport of angular momentum by waves, because there's a whole bunch of waves that are not the eigenmodes that you get from your Sturm-Liouville problem, right? There's also a whole spectrum of waves that transport a little bit of angular momentum and then get damped inside the star. And so these are much more difficult to observe because the waves are always damped, right? But they do impact the physics. And so there's really a whole lot going on here, which is fantastic and certainly not yet finished. We need to do more work. Now, on the chemistry, to couple back to the Mendeleev table and the chemical evolution models of the galaxy, well, the chemistry inside the star, let's assume you have all the chemical elements inside the star, and I've denoted them as X with a sub-index I. So this can be hydrogen, helium, carbon, nitrogen, iron, whatever, the whole table, right? It changes in time due to various phenomena, nuclear fusion, which depends on input from nuclear physics. And then there's the settling and the levitation that I've discussed before. And then there's all these macroscopic phenomena. So this is a transport equation, as we call it, that gives the change per layer inside the star of each chemical species that's inside the star. And we need to calibrate these three parameters here that you see. right? And so that's what really is the biggest unknown for now in the theory of stellar structure, you could say. So we are slowly starting to measure that, and we have quantified these levels of mixing for, about, here's a table with a summary, about 100 stars. But of course, there's stars with a factor 20 in terms of mass, with a factor 10,000 in terms of life phase. So what's 100 doesn't allow us to calibrate. We need way, way, way more stars. And what we do is distinguish the three different major zones of the more massive stars, because as I said in the beginning, these are the more important for the chemical evolution. So this is the stellar center schematically, and this is the surface where the arrow is, and then this is the core where everything is fully mixed. Yeah? Then there's a transition layer in purple, and this pink here is the outer layer where the radiation is stratifying layers that are not fully mixed, that are at a lower mixing level. And so the mixing levels are here indicated by these three colored regions, depending on different theories that we have, and among which we cannot yet choose for now because we have too few stars actually to do it. But so this table will gradually be building up dramatically in the next few years as we have learned now how to deal with asteroseismology of rapid rotators. And the more rapid the rotation, the more mixing you have. So now we can handle this. And I hope that, well, by the time I retire, there should not be 100 or 200 stars. There should be like thousands of them where we can code these mixing levels and quantify them. The work that has been done on how to do this and how to calibrate the amount of helium that is being created out of hydrogen is being led by two of my former PhD students called Johnston and Maegade Pedersen, and these are the updated papers that you see here. What have they found by estimating this chemical mixing? They find that on average, stars can have up to twice as much helium in their core created compared to models that we had prior to asteroseismology, where you assume no extra mixing is going on. So this has quite an impact, because if one generation of stars creates twice as much helium, from which you can then make carbon, nitrogen, oxygen, all the way up to iron, that means that the chemical enrichment is quite impacted. And so this was another surprise that we are now seeing from asteroseismology. Twice as much helium is easily possible for the stars that we have. Now what Cole did was turn that into a diagram that you see here, and this is the fractional mass of the core of the star as a function of the total mass of the star, right? And you see here stars that are calibrated by asteroseismology from gravito-inertial waves, right? And here there are binaries. That's another lecture. I will not do that, of course, but binaries, eclipsing binaries, also allow you to calibrate the level of mixing near the core of these stars. And there's actually a very good agreement between these two totally independent techniques. And the nice thing is then, of course, we have asteroseismology of massive stars that can give us internal mixing and the amount of helium that you create. We have binaries that allow you to do that. So what's the obvious thing to try? Search for starquakes in binaries, obviously, because then you have the two constraints together. This is still in its infancy. We're working on it very hard. Again, we first need our battery of machine learning to find close binaries that have stellar oscillations. Yeah? We have several of them. So what's the status of astroseismic modeling right now? Here's the recap that I have been telling you about. A major limitation actually in this whole scheme is that we are working with spherically symmetric stars while they rotate fast, faster than we anticipated in their interior, right? So there is up to a factor 100 discrepancy between the measured rotation rates and the theoretical predictions that is being fixed. And there is a lot of progress, really, on the theory to do that. Where there is less progress, because we have only recently been able to estimate these levels of mixing, we see that there's a wide range of mixing, and we have more stars before we see some trend, some tendons that we can then turn into a new theory of mixing, let's say, right? Another thing that I didn't discuss yet, but that's fascinating, is magnetic fields, because the Lorentz force, if we add that in addition to the Coriolis force, then we again get frequency shifts. These are even tinier than those induced by rotation, but we are now at a level that we can measure them. And so there are very few stars for which there is an initial measurement of the deep interior magnetic field of the star, which is also quite fascinating. We find a whole range of magnetic field strengths from 0 up to, let's say, 10 to the 6 Gauss, which is non-negligible anymore. So again, we have to go back to the wave equation, and we have to add an additional force due to the magnetic field. Now, what's a priority for me above magnetic fields is the fact that we have fast rotation, even deep in the star. That means that the star is flattened. And so we have to go to a new theory of at least two-dimensional stars in their evolution. This is very difficult. You have to do numerical simulations to get a handle on it. And so we're now trying to go from two-dimensional stellar structure models to one-dimensional stellar evolution, because the spatial scales and the time scales are such that even the most powerful computers of today cannot do two-dimensional stellar evolution from birth of the star until the explosion. But we do need to find ways to overcome this. And so this is a nice paper that tries to do this, that uses the centrifugal deformation of a star to describe the seismic waves. So now we lose our beautiful spherical harmonics because you have a flattened object in equilibrium. And that's a whole lot of mathematical complication, but very, very nice if you're a mathematician to try. And so what we would need is many more stars where we know how the effect is of the flattening of the star also on the surface properties. Because usually when we derive temperatures at the surface, etc., we still also assume in the atmosphere models that the stars are spherical. And so that gives a huge limitation. So the uncertainty on the abundances of the chemical elements at the surface is too large for the moment. I give here a plot with the carbon over oxygen abundance for stars that you see here in the interior of the star. So this is the center, this is the surface. Sorry, I'm mixing up here. This is an aging star going from birth to death, right? And so the abundances measurements that you see here have two big error bars. And so we also need to improve stellar atmosphere models that are being used to estimate the chemistry at the surface of the star. So we have lots of work to do. That's basically the message. And then, almost wrapping up here, but there's also the reality of people who do massive stars. And that's sketched in a simple graph that I made here. What does this graph show? A fraction as a function of stellar mass, and the stellar mass is a logarithmic x-axis here. So here's the sun, 1 solar mass, 1/10 of a solar mass, 100 up to 100 solar masses. This is typically the range of stellar masses at birth that you can have. You can be a bit more, but that's the ballpark. And this red line here tells you the fraction, the probability that your star at this particular mass belongs to a closed binary. So that means that you're not alone in the evolution, but you have two stars circling around each other where tidal forces come into play, right? And so you see for more massive stars that will explode later as supernova, so these ones in this mass regime, we're almost sure that they are in binaries, in closed binaries. So we cannot at all ignore tidal forces if we want to have a good theory of stellar evolution. So this is also something critical. For the sun, as you see here, you have about 60% chance for a star like the sun to be in a binary. So it's also, that's more than 0.5, huh? More than half of the chance that it's in a binary. Our sun isn't. And you see the gray areas are uncertainties assembled from the literature. But here, ignoring binarity is not a good idea. Well, this is what all astroseismologists are doing for the moment. Well, almost all, right? Now, some don't, some do better. And here's a beautiful example of a tidally induced oscillating star. So what you see here is the magnitude as orbital phase, and you see the beautiful measurements, each of these dots, and then a red line is sort of an average of the eclipse of the star. This is work by Zhao Huo, who has been leading this topic among many, many other people. Look at this, the long list doesn't fit the slide. Started in 2011, we call these heartbeat stars. You see, it's like a cardiogram. That's why they were given this nickname. But these are actually eccentric binaries, yeah, of revolving stars around each other. And when they are close to each other, then the tidal pull is much stronger than when they are away from each other. And we see this tidally induced oscillations. But we don't only see that, we also see tidally perturbed oscillations. What does that mean? That's something else. It means you have two stars. They each have their oscillations, maybe, and they revolve around each other, but they're far enough apart to just feel a tiny little bit of tidal force, but not inducing oscillations due to tides, just pulling in a different way so that the frequencies are changed. And then we discovered something new, several groups, tidally tilted oscillations in binaries. We had no idea that this existed. So what does that mean? It means that you have two stars. They rotate with an axis that we thought is perpendicular to the orbit. Yeah? But then it seems that one of them is oscillating in this direction. So these stars exist, and we have no good way for the moment in modeling them in terms of their internal structure. That's what we want, because the mixing in such close binaries in the deep interior of the two components will be quite different, because the wave equation now has yet another important force, a tidal force. Yeah? So we have a lot to do. And what we want to do, actually, is full astroseismology of flattened stars. This is not only a theoretical challenge, it is also an observational challenge. Why? Because if your star is flattened, like these ones, all of a sudden you have to care about how we as observers look upon the star. Because if it's flattened and we look at the edge, at the equator, then we see something different than when its rotational axis is pointing towards us, right? Becomes the hotter part becomes visible in our line of sight. And Altair here is an image of real stars. Real stars do this, they are flattened. Yeah? So I'm extremely grateful. When I was here last year, we got fantastic news that we have big grants from the European Research Council to try and develop evolutionary theory for flattened stars calibrated by astroseismology. So this is certainly something that will keep us busy for the next decade, until I retire, I guess. But we have to start at one point, because many of the stars where we have rotational frequencies, those between 20 and 30 microhertz rotation, they really are flattened. So we have to lift astroseismology to higher dimensions, as David introduced it in the beginning of the talk. So, to wrap up, for me, waves inside stars give a fountain of opportunities, as you see here. I could only discuss a little bit, but any topic in astrophysics, almost any topic, can benefit from the knowledge of waves, whether you search for extraterrestrial life on exoplanets, whether you do black hole mergers, whether you develop new instruments. The waves inside stars really allow us to get a much better handle on our knowledge.
I think I understand how the mixing inside stars affects the wave propagations. Can you just talk a little bit more about what the physics of the mixing are? These are different elements like hydrogen, helium, carbon mixing together, and why why does mixing create more energy and more light for a star?
Okay, so there are various phenomena. So you have, at atomic physics level, heavier elements sink and lighter elements raise. That's a slow process, we thought. But then if you do that in a gas that rotates, it turns out that the interplay of rotational mixing, as we call it, and levitating lighter elements is much more important than we anticipated. Right? Now, if you have a star that has, let's say, rotation mixes stuff, right? I always give you an analogy with a cup of coffee. If you pour milk, you're not going to wait because then your coffee is cold. No, you give angular momentum to your coffee and you drink it. So rotational mixing is dominant. That's what we thought. But these microscopic phenomena interplay with rotation and mix more efficiently. Now imagine, like for the sun, you have a helium ball surrounded by the pristine material at birth. But in this interface layer, there's more mixing. What does it mean? The hydrogen from the envelope gets mixed into the core, and the processed material, the helium, gets moved to the outer layers. And so you bring in more fuel for the nuclear fusion, which transforms hydrogen into helium only in the inner part where the temperature is high enough to do nuclear fusion. And that's why more mixing in the near core region brings in more fuel, more hydrogen, and so extends the lifetime of the star. And that's a critical thing to do age dating, right? Now, for stars like the sun, this is not important because the mixing of the sun's inner region is not influenced so much by rotation because it's so slow. But for these fast rotators, that's dominant. And we could only start to try and quantify it once we have a rotation measurement for these stars. Okay? Does that answer your question?
Yeah, so the mixing brings in the lighter elements into the hotter region.
Yes. Yeah. And brings the processed elements to the surface. Yeah.
So right now, most of the analysis is based on the frequency information.
Yes.
And there's also potential information on amplitude and lifetime of the mode, I guess, the width of the mode. With machine learning, one can imagine taking these large data sets and seeing at least if they cluster, even if our theory isn't yet ready to interpret the amplitude, whether there are patterns in the data that might be analyzed. Have people looked for that yet?
We are looking for that. I have courageous PhD students doing exactly that. And it's not so easy. Why? In the observational facts, the clustering is not very clear. So you have factors thousands between the amplitudes of some of the modes and others. But we do see nonlinear mode coupling, right? So we observe that. The theory is behind here. Why? We have to make the equations nonlinear. And that sounds easy, but it's not. So there are studies now of triple mode and higher mode couplings in a nonlinear wave equation. I didn't discuss that, but this is ongoing, and this is coming, because you are right. For now, we are only using the frequency information, and we're missing out on these beautiful amplitudes. So I think from a mathematics standpoint, we need like a couple of more years to do better, but it's coming.
Maybe you said, you may have said it and I just didn't quite assimilate, but you didn't talk quantitatively, I don't think, about the ratio of the axes in a star that's not spherical.
Okay.
What would be an extreme case, and is that determined from asteroseismology?
Yes, we're getting there, but very slowly, because we're only starting to do two-dimensional flattened sphere asteroseismology. In the extreme case, you have equators that are a factor 1.5 more than the polar radius. This is quite an extreme case where the star rotates near critical. But stars do that. Some do. And so we don't have a good handle on them by doing spherical harmonic-based asteroseismology. We really have to develop that. But this is easier said than done, but we're we're going to start. That's exactly what the new project funds are. So I'm happy. I'm grateful to the European Commission.
Well, Conny, great talk. Thanks for the good vibrations. So as you show here, waves inside stars can apply to many different regimes in astrophysics, right? Where do you think is going to be the most promising regime, and which one are you most excited about?
Oh, well, I'm most excited about massive stars. So I want to go to the binary evolution progenitors of gravitational wave emitters. That's where I want to be. It will take me some time. On the other hand, people who do exoplanet studies are all excited about finding extraterrestrial life, and they want to know mainly how their host stars affect the planets, right? People like yourself doing galactic archaeology, of course, what they are mainly interested in aging the constituents of our galaxy. And so for that, the red giant asteroseismology is really, I think, a great asset to what you can study in the sense of the galactic dynamics. Yeah? So for that, you do not need to upgrade the physics tremendously, because we are at 20% precision level in aging evolved low mass stars that are slow rotators. Okay, we can try to make 10% instead of 20%, but that's not the point for archaeologists of the Milky Way, I would say. So I think that chapter in astroseismology is very well developed. Well, the binary evolution channel is very poorly developed because it's the most difficult one, because of, you need all the forces, tides, rotation, and also magnetism, particularly for mergers, because they are very magnetic in their interior. Okay.
It's working? Okay. How do you know when the light is from inside the core versus when it's from the surface?
Okay, so that's a very good question. So we measure the seismic activity integrated from the surface of the star, but we know that the waves are propagating inside, yeah? And each wave, once you have been able to label its spherical harmonic, each wave has sort of what we call a kernel. A kernel is a mathematical function that actually encapsulates the probing power of each oscillation. And so the probing power of the oscillations that I was showing that give rise to this downward trend of fast rotators, these kernels of these identified modes, they are maximal just in the near inner core region of the star. So it's actually a mathematical integral equation that tells me where the probing power of each oscillation mode is. But you can only do that once you have been able to identify the spherical harmonic that belongs to each frequency. Okay? So that's a mathematical inference that follows from the theory of non-radial oscillations, actually. Right. I didn't go into any of these details. I could have, but that would have been a very mathematical talk.
So I guess one more thing. I know that because when light from the core usually takes, a long time to reach the surface. So there's a mix of like photons that are generated from the surface as well as from the core, and all at the same time, so created different points in time. So like there's this total picture, but like there's a time lag between the photons from the surface, created from the core versus from the surface, and you're able to actually break apart all of that.
Yes, but we're measuring, so the seismic activity is actually a measurement of the overall fluid elements that move up and down at the surface. Because by moving up and down, they become hotter and cooler, right? And so that's actually what we are measuring. And that, you could say, is an instantaneous measurement compared to the life of the star, which is millions to billions of years, right? So the time scales of the oscillations, even of the slowest oscillations, is still nihil compared to the lifetime of the star, right? So that's how we can unravel these two, right? And that's why multidimensional simulations make sense, because these are snapshots at a certain moment in the life of the star where you can have way more resolving power in spatial and time dimension. And so that's a specific type of study by itself that is part of my spinner that I'm not good in, but across the street they are.
I'm sorry for asking a crude technological question after your beautiful presentation in basic science, but are there applications of asteroseismology to the development of nuclear fusion reactors here on Earth?
Well, let me say that there should be a good interaction. I will tell you what we did 2 weeks ago in Leuven, actually in Belgium. I put people, nuclear physicists, together in a room with astroseismologists and with spectroscopists who measure abundances, surface elemental abundances of stars. And we came to the conclusion that the uncertainties in the nuclear reaction rates, mainly for neutron star mergers, are so uncertain from the theoretical physics point of view that they compete with the uncertainties of the mixing that waves can calibrate. So I would say that for close binaries that are going to have 2 supernova explosions and then gravitational wave emission because of the merging of neutron stars, there we have to interact. And that's certainly something that needs to be done. It was sort of a first time that these 2 crowds were talking to each other, and it was very fascinating. Nice. My knowledge in nuclear physics has grown since the past 2 weeks, but it's not enough to say the exact directions, but I leave that to the specialists.
I'll add, because one of the things we do is support a collaboration looking at the stellarator design. And today's talk was at the surface of the star, the photosphere, where the light comes from. Mm-hmm. One can go further out beyond the photosphere to the corona, where there are very strong magnetic fields and reconnection going on. And there's actually a very healthy interaction. Some of the same people who think about reconnection and field confinement are thinking about stellarator design. And it's actually a little bit further out from the photosphere where this interaction is, this intellectual interaction is taking place.